Hello and welcome to Lecture 2 of Chemistry for Interdisciplinary Sciences. This is a sort of add-on really to the last lecture where we were talking about electronic structure and where the electrons actually are in an atom. Today we're going to sort of prove what we're talking about and talk a little bit more about that colour demonstration that we saw last time. So here are the learning outcomes. We're just going to make sure that we understand about the energy that it takes to move electrons around or remove them completely from an atom. We're going to have a look at what exactly is favourable when it comes to electronic configurations, and also talk about that colour demonstration and think about why are there energy levels in an atom and what causes that to happen. So let's go back for a second to sodium. So we saw sodium in the demonstration. In fact, shall we just pop over and have a quick look at that demonstration again? So here we have the alcohol burning there. It's methanol specifically burning with some chemicals in there, some specific elements. And you can see that the flames change colour based on which element is in there. Now, sodium has a really common yellow colour. I believe that's the sodium on the second beaker there. So there you see a red one. Every element has a really unique set of colours that they output when they're in a high energy situation like this. And this kind of proves the existence of orbitals and the energy levels that we were talking about last time. So there's sodium, there's boron, nice green flame there. So what does that actually physically mean about the atoms themselves? I'm going to pause that. So sodium, we said, had 11 electrons. We knew it had 11 electrons because it has 11 protons. And the protons are positive, electrons are negative. They're going to attract as many negative charges as there are positive ones. So because we have 11 electrons to put away, we might do that in the simple electronic configuration of 2, 8, 1. And again, this all goes back to the periodic table. Sodium is there on the third row in the first position. And that's what tells us that it is a 2, 8, 1 configuration there. Third row, 1 position, first position, so 1 electron in the outside shell. We then suggested that we could break it down a little bit more because the periodic table actually has a more complex structure. Sodium is over there in the S block, all on its own in the very first column there of the S block. And so what we would expect then is that its outermost electron, which we'll call the valence electrons, are going to be in an s orbital because the element is in the s block. That is what defines what an atom behaves like, essentially. What orbitals are the electrons in? What do they have available above them? Do we want more electrons inside that orbital? That's what we're going to talk about today. So a quick reminder about how we do that. Basically, if we wanted to do sodium and figure out sodium's full electronic configuration, we pass through each of the elements on the periodic table. It tells us how many electrons fit into each of the orbitals and so on. So for sodium, we go past 1s, so we go past 2 elements in that block. Then we go past 2 elements in the 2s. Then we go past 6 elements in the 2p, and finally in the 3s we're in the first position, and that's why sodium is a 3s1 electronic configuration. And a very quick reminder that it carries on like that, 3p, 4s, and then the next one down is the 3d orbital. So a quick reminder that is about essentially how often the phase changes there in the d orbital, so the fact that it's peak trough all the time costs just a little bit more energy to get into that orbital, and the 4s and the 3d just so happen to overlap. So what do I really mean by that? Well, I'm saying that the configuration of the electrons is going to define how many electrons are needed in the future, essentially, or how many electrons that atom would be stable with, losing or gaining. So we have a look at chlorine here. Chlorine, if we pop back to the periodic table, is there in column 7, so in group 7, and it's in the third period, so it's 3 rows down. So chlorine must therefore have a simple configuration. If it's the third row, it must have 3 shells, and if it's in group 7, its outermost shell must have 7 electrons, hence 2, 8, 7. Or if we were to break it down using that whole process again, chlorine is there. So that means that it goes all the way through 1s2, 2s2, 2p6, because there's 6 elements there, 3s2, and chlorine is in the 3p5 electronic configuration. So that's the structure that we got down there, 1s2 and so on, 3p5. Now, chlorine is right next to an element that we know is relatively stable. So we pop back to the periodic table. Its chlorine is next to argon. So the electronic configuration of argon is unreactive. Remember we mentioned right at the start that those noble gases, the ones that don't react with anything, must not want to lose or gain electrons. That must be quite a stable configuration. And I'll remind you again, what it means is that we have full spheres of electrons around the nucleus there in their little wave patterns, like that p orbital or like the d orbital there. So the fact that chlorine only has 5 electrons in its outer shell means that there's a little sort of empty hole in its outermost orbital. If it's 3p5, we must have 2p orbitals that have 2 electrons in, and then 1p orbital that only has the 1 electron in. Remember again, orbitals can hold 2 electrons because of magnetism in there. So when chlorine reacts, it's going to try and gain electrons in order to become more stable. Now, what do each of those different levels actually mean? Well, the reason that it fills up first, 1s2, then 2s2, 2p, and so on, is that each of those different paths represent a different amount of energy needed to occupy that energy level. Remember, again, we talked about waves and wavelengths and the fact that different wavelengths mean different energies. Well, remember that we said that only very specific wavelengths around an atom can make up an orbital because it's got to have that sort of repeating structure there. So that means that if we think about a 1s orbital, but just a sphere, then it's got to have exactly the right wavelength to orbit, if you want, the nucleus there. And it has to have that single perfect wavelength. A longer wavelength would mean that it's not a single repeating cycle. We go back to that fried egg shape there. And shorter would mean the same. So there's only one perfect wavelength there. And so we say that there's a certain amount of energy required to be in that particular orbital. And then the next one up would be the 2s. That's the next one we fill. If we look at this configuration, 1s2, 2s2. 2s is next. It must be higher in energy because the 1s fills first. And then the next one up, 2p, must be even higher in energy, and so on. That's what forces the properties of the periodic table, really. It's the fact that the orbitals have to be filled in that 1s2, 2s2, 2p6 order there. Now, what does that physically mean? Again, these energy levels represent the perfect wavelengths that an electron would need in order to complete that cycle. And of course, the wavelength depends on how attracted the electron is to the nucleus. The more positive the nucleus, the closer the electron might want to be, and therefore the easier it is to get in that wavelength, or the smaller wavelength you need, and therefore the higher energy, whatever it is around that element. It's all defined by the nucleus. And so while all the energy levels will follow this pattern, 1s first, then 2s, then 2p, and so on, the more protons there are in the nucleus, essentially the more squashed together these energy levels will be, because now it's going to be even more favourable to be in a 1s orbital really close to the nucleus for a negative electron to be attracted to that positive, and then it'll be slightly more favourable for the 2s, and so on. So I want you to think about then these orbital paths, and again remember we're talking about these waves, these repeating symmetrical waves, a bit like a motorway almost. There are specific paths that those electrons can follow, and it costs you more and more energy to get up. In the slow lane, you might be hanging out at 60 miles per hour. In order to get to the next lane out, where things are going a bit faster, you need to push the accelerator. You need to add energy to your vehicle, wherever it is, so that it goes faster. And if you want it to change from 70 to 90, you need to put in more energy again. Doesn't matter how many cars are on the motorway, there are always 3 lanes. And it's the same for an atom. No matter how many electrons there are always empty these orbitals, these possible electronic paths that the electrons can take, assuming that they have the right amount of energy, or rather they have that perfect wavelength, which is related to energy. So you can imagine, if I'm going from the 60 mile per hour lane to the 70 mile per hour lane, I've got to add 10 miles per hour into my car. I have to add that very specific amount of energy, assuming that the lanes were very specifically these speeds. And to go from 70 to 90, I've got to add exactly 20 miles per hour's worth of energy to the vehicle. And to go back down again, that energy has to be given out, doesn't it? The 90, if you're going at 90 miles per hour and you're going down to 70 miles per hour, you have to put on the brakes, you have to expend that energy in the form of heat, and so that you can go back down into that 70 mile per hour path. The same is true for an atom. It's got all these different energy levels over here, and it's the 1s, then the 2s, and the 2p, and so on. If I have an electron in the 1s energy level, it's a bit like having just one car on the motorway. It can still go onto those faster lanes. They're still available, and that's what's happening in the flame test. When we have a look at these elements, their energy that's being given to them by the fire, essentially by the methanol burning, is promoting electrons from their valence configuration, i.e. where they naturally would be, up to some higher position. And so that might be represented here. We've just got hydrogen, haven't we? 1s1. So we got this electron being promoted up to, say, the 3s, for instance. But it could be any of these possible wavelength paths for the electrons to travel. Could be any of these. But remember, again, they are specific in energy because it's got to repeat. Can't be longer or shorter than whatever wavelength gives them a perfect symmetrical path. So going up from the 1s to the 3s, that is basically inputting energy to the atom in the form of heat. You can do it with light as well, with a laser or something like that. You put in your energy to that electron. It hangs out up there in that higher energy level, which is the 3s in this diagram here, but it can be any of them. And then you imagine that that electron eventually wants to drop back down to its normal state, back down there at 1s. Well, in order to do that, it has to expend energy, just like we talked about our cars, expending that energy in the form of heat on its brakes. An electron expends that energy, gives that energy out in the form of a photon, basically a packet of energy. And the amount of energy in there, so I'm calling this the delta E, the change in energy. That's what this triangle means. It means change in energy. The size of this energetic gap is going to be related to the frequency of the wave, or, as we've seen before, the wavelength. So what I mean by that is, the larger the gap, the more energy your photon that's given out will have to give out. It's the same as going from 90 miles per hour down to 60, as opposed to 90 to 70 there. So the larger the gap in between the energy levels that we're seeing up here, the larger the gap, the higher the energy of the photon, and therefore, remember, the smaller the wavelength. So again, this is a higher energy wave than this. So the two are related here by these two equations, and you do need to remember this bottom one mostly. So what this is saying is the change in energy is equal to, and then we have two constants here, H and C. They are Planck's constant, which will be given to you in an examination or something like that, and will be given to you in workshops and so on. And another constant, the speed of light, C. Again, that would be given to you. And that would be divided by the wavelength. So what I would expect you to do with this equation is rearrange it to find out what the wavelength of a certain photon with a certain energy would have, and also vice versa. So what wavelength a photon with a certain energy would have. And again, I'll just remind you, H and C are constants. They will always be the same number, and they will be given to you. So it's a relatively simple equation to rearrange. But what I'm saying is, the larger the delta E, the larger the wavelength. Does that make sense? No, the smaller the wavelength, because it's a divide, isn't it? Let's just think about that again. If I've got this value, Hc, which is constant, and I divide it by a bigger number, a longer wave, then I should expect to see a smaller energy, a smaller gap. And vice versa. The bigger the energy, well, therefore, the smaller that wavelength must be, because I'm dividing hc by a smaller number to get a bigger energy. So it's well worth you just plugging a few numbers into this and just having a look at it and seeing if it makes any sense. Up at the top, we have a slightly more simplified version. Delta E equals hf. Here, f is the frequency. You might also see f represented as a v. Well, it's a mu, I think, actually. hv is usually how it would be written. Frequency is the number of waves completed per second, and light always travels at the same speed, the speed of light. So the more waves you complete in a second, the higher the frequency. So this is a high frequency wave going like that. And this is a low frequency wave. In the same distance that I'm drawing here on the screen, I'm completing fewer waves than if it was higher in energy where I'm completing more. So frequency is measured in hertz per second. It's saying how many waves per second in that time. So I said that I'd prove what I was talking about when it came to these energy levels and prove their existence. Well, if we have a quick look at the ionization enthalpy. So the ionization enthalpy is the energetic cost to remove an electron from an atom, an elemental atom as well. So here we've got increasing atomic number, and here you can see how much energy it costs us. So hydrogen has some, let's just call that the middle value. Hydrogen with just one electron around it is willing to give up its electron a medium amount, let's say, because it's in the middle of this axis here. When you go to helium next, that energy goes way up. It becomes much more unfavourable to to remove that electron from the electronic structure itself. So that being the case, that must represent a more stable configuration. Helium, with its 2 electrons in its first shell, must represent exactly what all the other atoms want, because it's the hardest to pull the electrons off. As you go from helium, so we've got hydrogen, helium, these black dots, to lithium down here, that's this bottom one, this yellow one, all of a sudden it becomes really easy to remove an electron from lithium. Why is that? Because once you've removed an electron, it has only one s2 configuration. It has 2 electrons in its first shell, which is exactly what helium has, and it's so stable. So when lithium loses that 1 electron, it becomes more like helium, and therefore more stable. It goes up and down and up and down. We're going to look at that specific structure, but let's just keep going. So we've got lithium, beryllium, boron, carbon, nitrogen. Goes down when it comes to oxygen. We're going to look at that in a second. Fluorine, and then neon is the next one here, up at the top. So we've got helium, neon. It's not going to surprise you that that's argon there. And then we've got krypton next, and xenon. So all of these peaks here in the ionization energy is suggesting that these are the most stable electronic configurations. And again, that tells us what an atom is going to be trying, quote unquote, to do. And by that I just mean it's the most favourable position for our electrons. Just very quickly going to plug this in. Okay, so what about that more complex structure? What about here in this where it goes lithium, beryllium, and then boron all of a sudden? So what does that suggest? If that one is beryllium and then that one is boron, if that's beryllium and that's boron, it suggests that boron is easier to remove an electron from, which suggests that a 2s2 configuration, which is beryllium, if we just pop back to our periodic table, beryllium is there in the second row and the second column. So that suggests that that's a relatively stable configuration compared to boron, which is over there on the other side in group 3 in the P block, right next to it. So that suggests that, one, full shells are really favourable. That's why they're all very high in energy. It costs us energy to remove electrons from those configurations, but it costs us slightly less energy to remove electrons from boron, which suggests that a full orbital is also relatively stable. So a full shell is good, i.e. a whole row of electrons, but if you can't have a whole row, then a whole block is good. If we keep going, so that's boron there, carbon, nitrogen, And then down oxygen. So we think about oxygen and we have a quick look at the periodic table. Oxygen is in position 4 of group 2. So that means that it must have a 2p4 electronic configuration. If it's 2p4 and we remove one electron, then it becomes 2p3. Now, why is that more favourable than 2p4? You see how the fact that it costs us less energy to remove an electron from oxygen suggests that nitrogen's configuration is relatively stable. Again, we'll just pop back. Nitrogen's configuration is 2p3 in its outermost valence orbitals. So that suggests that a half-full orbital is also relatively stable. Why is that? Because we should have 6 electrons, shouldn't we, in the p orbitals. Nitrogen in the 3rd position is more stable than oxygen in the 4th position, i.e. 1 electron in each orbital is better than 2 electrons in one orbital and then 1 electron in the other 2. All of this is to say that a full electronic configuration, a full shell, is primarily what an atom is trying to do, a full shell if it can. But you can only really gain and lose a certain number of electrons. So if it can't do a full shell, i.e. a full row, then it'll do a full orbital. And by that I mean a full block instead. So just the little sections of the periodic table. If you can't do a full block, well then you're going to have to do a half full block, and that's the next most stable configuration. So let's have a quick look at how that actually comes out when it comes to elements. Here we have sodium. Sodium's electronic configuration is 1s2, 2s2, 2p6, but most importantly it's in the 3rd row in the s block in the 1st position, so it's 3s1. Notice that basically we've got a full shell here, so if I just change that to a pen, I'll just change the colour. All the way up here we've got a full shell. That's a full shell. And then we've got this one extraneous electron just hanging out in the outermost shell, not being full in any way. And there it is, that electron there. Boo to it is what I would say. If we look at the chlorine, it's 1s2, 2s2, 2p6, 3s2, 3p5. It's in the 5th position in the 3rd row of the p block. So that's not a full shell yet. Notice, look, we've got this little hole here that we would like to see a little bit more of. So what's going to happen is the sodium is going to give that electron up to the chlorine. So we'll just watch that again. Sodium has that one extra electron in its outer shell, doesn't really want it, so it gives it over to the chlorine. If we erase all the ink for a second and we think about that, sodium has lost an electron. Electrons are negatively charged. So sodium must now have one more proton than it had electrons before. You need to think about that really carefully. It's completely backwards to what you would logically think. When an atom loses an electron, it becomes more positive. So the sodium will become Na+, and its electronic configuration, 1s2, 2s2, 2p6, that's the same as neon. Perfect, that's great. That's a stable electronic configuration, we know that. The chlorine has gained an electron, so now it has one more electron than it has protons, which means that it's negatively charged. So if it's negatively charged, that means that we must therefore have one extra electron in the outermost orbital. And again, 1s2, 2s2, 2p6, 3s2, 3p6, that's also a full shell. So in this process of switching between those two, so that electron going over there, what we've done is stabilised both atoms. Sodium has given up an electron, chlorine has gained an electron. This is fundamentally the difference between a metal and a non-metal, and we'll talk about those in lecture 3, I think. But for now, hopefully that makes a little bit of sense to you. Both atoms have ended up with an electronic configuration that has a full shell, and that is a favourable thing to happen. Great. So that takes us to the end of that idea there. Hopefully at the end of that you appreciate that we've got electronic structures, that there are electronic configurations that are stable for some and unstable for other elements. So you're trying to get to a full shell, a full orbital, or a half full orbital, in that order. Brilliant. So that takes me to the end of it. I'll see you in the next lecture.